Hello, everyone. Welcome to the webinar. Dr. Kalana Withanage. And in this webinar, we would be covering a few topics on computer vision, basically concepts, application, trends, and opportunities. And to begin with, I will start with playing a small movie clip, which is Terminator, which was released in 1984. In this particular movie, certain computer vision techniques are demonstrated, such as segmentation, object detection, face detection, that sort of thing. But quite frankly, by that time, things were not quite ready. The techniques were quite unreliably working. Actually, computer vision took long to fly off. Actually, flight off only within the last decade or so. And yeah, so we'll have a look. So that's detecting some objects, segmentation, some optical character recognition, person detection, matching different clothes, kind of face recognition. And face detection with the landmarks. Yeah, by the time this film was released, things were quite not ready, but it was more futuristic. But with this film, I think you could get some grasp of the ideas, what I'm going to talk about. So now we're going to look into some computer vision concepts. The subject itself, sometimes termed as machine vision or computer vision, or you can call it as CV or MV. The computer vision subject is correlated with other artificial intelligence subjects such as machine learning, deep learning, robotics, neural networks. So it is among the friends of artificial intelligence, I would say. And if we take the computer vision itself, it is a multidisciplinary subject which has components from physics, mathematics, artificial intelligence, image processing, pattern recognition, and signal processing. So if you look back to the time scale of how things were happening for computer vision, the early stage of computer vision was in like 1970s, where things like simple shape detection was and things like line detection was tried on. And 1980s, late 90s were kind of image processing were done for factory inspection sort of thing. And to be honest, actually the computer vision become more reasonably usable solution within last decade or so. So it is quite a accelerated journey for computer vision. So it's an exciting time. Before we go more details into the computer vision itself, I would like to have a bit of understanding into human vision system. Human vision system comprises of a pair of eyes, and we do have the brain itself. So whatever the objects we see through the eyes are creating an image in the retina, in the eye, and that is translated to electrochemical signal and transmitted via the optical nerve into the visual cortex. This visual cortex is kind of processing part for the brain for the images, and some scientists say like actual visual perception. Visual perception is understanding of things that we see, is actually comprises only 20% of actual image, and 80% of previous memory, imagination, and experience. I'm not sure about that, but it's quite an interesting factor. Certain things, visual tasks, I would say visual tasks, such as reading a book, identifying different objects, driving a car, that sort of thing needs visual capabilities. These tasks are quite with a relatively easy task for human to do, but teaching the computers to do so is quite painful and unreliable. Now we are having a comparison between human vision system and computer vision system. In the human vision system, as I said, there's a pair of eyes and the brain. Similar to that, similar to the eyes, we have the cameras in the computer vision system, and some sort of processing element or a computer for image processing is there. Other than that, the input and output. In this case, the image of the fruits is the input, and the output is the interpretation of what those are. So that is same. That what's in the middle is in change. So the key part of key starting point of any vision system is the camera. There are various kind of cameras do exist. These vary by different lens attribute like focal length and the field of view. Field of view is the what sort of angle it can cover, and sensor technologies, CCD or CMOS, and what sort of frequency spectrum the camera is sensitive to. Most cameras are sensitive to visible light, but there are some more sensitive to infrared or ultraviolet, or X-ray, that sort of thing. Or there could be like logical cameras, like, for example, a CT scanner is not a really camera, but the output it produces is an image. So it is also, we can consider this as an imaging device. And these cameras could be either fixed or moving, could be mounted on a mobile platform. It could pan or tilt or change the zoom, or they could be cameras which could be a bundle of cameras stacked together. For example, in 360 is a the distance to the object as well. This could be through stereo cameras or special 3D cameras. Now we look into the camera construction. Each camera do have a kind of lens, and there's an imaging sensor, which is a matrix of different small sensors, and there's a kind of chips around. So when the lights comes to the lens, it is focused on into this image sensor, which is the critical part of the conversion, which converts the light into to an electrical signal. And this electrical signal is eventually encoded into an image. Image is basically we could visualize as a matrix with and it's a smallest component we could say is the pixel. So for a camera, the resolution is the x multiplied by y. It's the resolution for a camera. So now we consider one particular image taken by a particular camera, In this case, for the simplicity, we could consider it as a black and white image. And so the image is basically a set of pixels. In this case, we can see it as small squares. And this most black pixels could be having a value of 0, like here, and then up to 255 for the most whitish pixels. So for each pixel, we could the different values are assigned from 0 to 255, and what computer sees is actually a set of values in a matrix. That's all the computer sees. It doesn't see the image what we see. It is a set of values. So it's quite impressive just by looking at these values. Computer vision tries to interpret the world around that. It is very fascinating. Okay, so now I'm going to introduce you few more concepts. One key concept is the edge detection in computer vision. If we have done any conversion for a sketch for a colored image, which creates a edges for the black and white image. So consider this example, and these are the values assigned to each pixel. And each pixel is a we call a jump in its intensity value. A high jump in its intensity value, we call it as an edge. For example, from this 23 to 103, it's a big jump from the value, so we can mark it as an edge. Similar edges exist there, so we can mark it as an edge. Likewise, so for any neighboring cell, consider this pixel, and we could have neighbors around that in a vertical or horizontal direction and diagonal directions. And when we scan through, we can see whether there's a significant increase or significant changing of the intensity value. We could mark it as an edge. And in this case, for example, if you consider this pixel in this direction, there's not a difference, or 99 and 103, there's not much difference. So by a threshold, we could say, oh, it's not an edge. So once we do this operation for all the pixels, we can scan through and do the same operation. We could identify some edge. So it's fascinating. So now you have manually done some computer vision. It's a kind of first step, baby steps in the computer vision subject. These computers needs to understand various geometries, like the simplest form geometry could be line. When we provided a line, usually it is converted into a black and white image, and there's different mathematical matrix operation which can be scanned throughout the image, which could give an indication of whether there is a presence of a line in the image. For example, in this image, if we run through this line detection algorithm, it could detect there's a line here. Similar to lines, there are the different geometrical shapes, like rectangles, triangles, circles, such on. So there are different mathematical filters to detect these ones. It's quite fascinating to do this simple identification of the shapes. It's a very early development of computer vision, but it is simple, but it does something great. So when we come to the real world objects, or things like humans, faces, the simple shapes didn't work quite well to identify them from one to another. So so people come up with something called features and feature vectors, feature descriptors. Feature descriptor is a collection of features, and for your simplicity, you could imagine it as a kind of pattern. So, so for this image, this is a pattern for the person, and if the system can detect there's such pattern in the image, we could say it is a positive presence of a person. So, so features and feature descriptors is a kind of main thing in modern computer vision, which is helping to recognize different objects, faces, human poses, a lot of things. So it's a key concept. And these computers, we need to let them know what are the say we are going to identify, say, orange and apples, and we would have two set of images, data sets we call, for the oranges and the apples, and we have to label them as apple and other as oranges, and then we could extract the feature vectors, and these feature vectors are fed into a classifier, and classifier could indicate whether this is an orange or an apple. In this case, we could first go through the traditional way of how it is doing. We could have an input image, and which is a car, and initially this feature extraction was initiated with man-made models. And once we calculated the feature descriptors, we feed it into the classification algorithm. Then it detects it as a car or not car. With the introduction of deep learning, it combined this feature extraction and classification together into one set of multi-layer neural network. What the beauty it did was, like, for identifying different objects previously, different people have come up with different different models for the beauty of the deep learning is what we input into the system is the image itself. We don't provide the computed feature vectors. We provide the raw images, and the deep learning would figure out what is the best representation for this image, and it would identify how to differentiate one set from another. In this case, it's a good example for showing you what different things are happening in the different layers in a deep learning multi-layer architecture, where initially we input only the raw image, and in the next layer is identifying different edges in the image, and next thing is a combination of edges, and the third one is a more combined of surfaces. In the initial one, it had only the edges, and edges were comprised into more detailed one. It is comprising a more high level thing. So in training a classifier, we would have different data sets with one data sets for the presence of the particular object or something, and others. So that would when you feed that in network, it would train a model. This model variables get changed, parameterized, and it creates a pre-tuned model. The tuned model is the one we use for the actual real-time thing. Because this training could be done offline. It could take weeks or months to train a proper model. Once we train that, usually this pre-trained model is possible to run at real time nowadays. So for any test image, we compute the same features and then feed into the pre-trained classifier, which would then detect whether there's a presence of a particular object of interest. Yeah, as I said, this previous the training part is mostly offline, but the actual testing is kind of real time. So now we see a video again with pre-trained model to identify different objects in a video. So it detects persons, cars, dogs. Yeah, so it is a very important thing to identify the objects around us by the cameras. The next concept I want to introduce is the optical character recognition, which has been there for a while. The idea behind this is to the computer to identify the text around that. It could be digital prints or could be handwritten text or in signage board. The concept of working is like you would have a raw image, and which is converted to a black and white image, and then split it into different characters, and each character is sent through a classifier to identify what character to interpret that as a character. It is a very important skill for the computers. So in this demo, we would see how these cameras are going to read the number plates on the vehicle and read it out as a text. It's a very important skill for the computers. Now, with the two techniques I mentioned, computers can recognize the objects around that, and also it can read the text or some language around that. Is important. Next thing is it needs to understand the faces around computers. And there's two terms I want to introduce. One is face detection and face recognition. Face detection is kind of object detection, object recognition. Portion of who the person is the face recognition. So it's a difference between face detection and face recognition. So for any given image, first task is to identify the faces, where the faces could be, and then for each face area, we would run through a kind of facial landmark identification, which would create a feature vector for the face, and with some pre-trained model for that person, we could see whether this is person A or person B. Now, in this demo, we are seeing how this is being applied to identify different persons. Okay, now computers can identify the faces. And next thing is it needs to understand the actions of the persons. Um, so what it tries to do is it tries to identify different body parts and um, then uh, then kind of find out the where these are located, and with the prior knowledge of the person's skeleton anatomy. For example, the torso is connected to the legs, upper legs, and upper legs connected to the lower legs, lower the foot, so wrist, and here for the elbows, elbows are detected with the computer vision. And in this case, the same person is on the flip side. Yeah. So what we try to understand is the positioning of the each different body parts, and try to figure out a skeleton matching for the person's image. Actually, in my PhD research, I have spent a lot of time with this subject human pose estimation. It was quite fascinating to me. And in 2013, solution were like somewhere between 50 to 60% of accuracy. And within a time period of like 5 to 6 years, it was improving massively. And seeing this sort of video was very inspiring to me. Have a look. This is identification of different body parts, which is not the final result, but it is interesting to see the intermediate results for your understanding. Yes, so now computers can recognize persons' posture and activities. Now, we have learned about few concepts starting from object detection, optical character recognition, face detection, face recognition, and human pose estimation, um, and action detection, recognition sort of activities. Now, for it could look like simple, but there has been a massive effort by a lot of researchers around the world to get this up to this stage. And even with that, there's a lot of issues could happen in reality. Like what we need to understand what these realities are. One reality is the illumination and lighting condition. For example, consider this car. The car's headlights are on, so other than the headlights, we cannot see much around that, all being dominated by this headlight. And in this case, similar, the sunlight has dominated and you can't barely see anything else. In this scan, there's an expiry date printed, but due to the bad lighting and the lighting condition, we cannot really see that. And in this case, there's a kind of polythene cover on the barcode, and due to the illumination and shining, it could be affecting the detection. And another issue with that, all the computer vision techniques, is the viewpoint variance and the pause. Because for example, consider coffee cup, which could be seen from different angles. It could be seen from upper top view, or could be from another. Is when it comes to people, things like people can be in very weird formation, and it could create. It's different to detecting or recognizing a mug. Mug is a kind of rigid object, and person could be having a lot of different formations. And one other difficulty, consider this mobile phone. It is hidden by the person's fingers, hand. So we just see a part of the mobile phone, and we have to figure out what it is from just the partial view. And consider this clutter. There's a cat lying on a similar background, and I can barely see the cat. If I don't see the eyes, it's quite difficult to say there's a cat here. Even to the human, it could be becoming difficult. So these are difficult conditions for computer visions to face. Okay, so we learned about a few computer vision concepts and what are the difficulties it could face in the real environments. Now we're moving into some computer vision applications. In a nutshell, I would say anywhere that you could use your eyes and solve a problem, it is a possible candidate for computer vision to be applied. I think I'm talking on different verticals. Firstly, I would take two technological verticals, robotics and augmented reality on VR. This is different to other business verticals I'm going to talk about, but I thought I need to talk about this first because there's a huge amount of effect into these two fields, robotics and augmented reality from computer vision. I would say these two fields are heavily going hand with computer vision. Robots are inherently having a mechanical dynamic structures, and those are meant to move around. But if robot need to be intelligent, it needs to know its environment around. This capability is given by the perception. It needs to understand the things around. But perception is a hard thing to do with the traditional sensors, like say ultrasonic sensor, or other normal previous things. But camera input is a very rich input, which could be used to interpret the world around, which is very useful. Previously, the computers were programmed to do exactly the same thing over and over again, but nowadays, due to the smartness it gets through the perception, it could work in an unstructured environment. We call it in the wild. I would say there are three key capabilities robots needs to have to make it autonomous or self-intelligent, smart. One capability is the localization and mapping, which is identifying itself where it is within the environment and create a map of where it is so that it can move in between different parts of the surrounding. Another thing is the human-robot interaction. if the robots needs to interact with the human, it needs to recognize the persons first, then recognize person's actions, eyes, gaze, and intentions. And last thing is it needs to identify different objects around that. So if it could identify, say, a mark, it could grasp a mark. If it could identify a ball, it could grasp a ball. So so identifying objects, humans, and identifying where it is are three major. So these capabilities are only possible through computer vision. So in this demonstration, it is showing this robot is moving around and creating a map of its surrounding. In this white color thing, you'd see it's slowly creating a map. It's not really like that because it has to move around a few bits to create a real map. This situation is typically called as simultaneous localization and mapping, because when the robot is first introduced into the environment, it doesn't know much about the environment, so it has to first create a map. At the same time, it doesn't know where it is exactly within the map, so it has to determine where it is, and it has to create a map at the same time. So that is why it's called simultaneous localization and mapping, or simply called SLAAI. So it's now creating a bit of a structure. In the blue color, you'd see. Let's see how it is shaping up. Okay, now it's look like a room. So it has finally created some sort of map for the environment where it is, and you can see where it is as well. In another one capability is the human robot interaction. In this scenario, the robot monitors whether the person is paying attention or doing something else. If the person is doing something else, it pauses what the robot is. Robot pauses what it's doing so that it doesn't accidentally damage the person. So it's mutual understanding between robots and humans. And in this demo, the drone is moved around and it's creating a 3D reconstruction of a statue. Which is only possible with the 3D reconstruction with computer vision. So we have seen few capabilities where computer vision being very useful in robotics field. And here's another example. In this case, the boxes are moving, but it doesn't care about the boxes. We don't need to worry about the boxes' actual orientation. Robot would identify its orientation and it will pick accordingly. In previous generation programmed robots, it needs to be sent out exactly the same way, otherwise a robot could miss the box. So in this case, this robot is smart enough to identify the box's orientation and act accordingly. Okay, now we come to the augmented reality and VR. Augmented reality name itself is coming from augmenting a reality, which is we are combining the real reality with a virtual reality rendering. In doing that, so we are creating a virtual world within the real world. So in order to augmented reality to do this, it first needs to understand what is surrounding and where the position of each object and persons. Then only it can actually render something on the object or the on the particular scenario. In this the HoloLens, you would see some cameras. It will see the things in front of that, and then computer vision is run to identify things in front of that, and some projection, like in this image, is projected into the lens so that a person would see some alternated reality within the real environment. So this is only be possible with the application of computer vision. I would say augmented reality is nearly impossible without computer vision. Let's have a look into a demo of HoloLens. In this case, the person is interacting with a real thing, and he's provided additional information on his HoloLens. And in this case, the person is interacting with the virtual body on a table, on a real table, which helps to medical people to understand the body clearly. Okay, now we come to another vertical, which is agriculture, which is important. We need to be fed. So starting from the initial soil and land preparation, the computer vision helps to identify soil and land condition, and it helps with weed detection, spraying, crop monitoring, diagnosing different plant conditions, then helping harvesting, and helping sorting out different category of food, tracking different livestock and monitoring them, and all the way up to the supply chain as well. For example, in grasping these, harvesting these grapes, these robots need to identify where the grapes are, and then it can dynamically keep its gripper around the stem. And in this, with this drone, it's identifying where the weeds are in the field. Then it could help the farmers to do something accordingly. In this case, the apples are being detected with the computer vision. This demonstration shows how the computer vision is applied to detect weeds. And identify different types of weed. Yeah, so it helped the farmers to keep their farmland tidy and clean, and maintain the standards. Okay, so another application of CD to detect apples, which could help to identify the yield, what sort of crop the client would expect, and yeah, you could monitor the field for that. Okay, another application is sorting, where different types of apples are sorted according to color, shape, color, size, and the different types. And into the livestock tracking. In large farmlands, cows could be in large farmlands, it's quite difficult to track this sort of livestock in a large farmland. So this could help to do it with, for example, with drones. Okay, now we come to the application of CV in computer manufacturing. Um, uh, in manufacturing, starting from autonomous robot in the factory and human-robot collaboration, and make sure in work safety compliance and sorting, QA inspection, supply chain tracking. The, the applications of CV are in every aspects of modern day factories and manufacturing facilities. In this case, this robot picks different plastic parts from the conveyor belt, and it identifies the orientation of each of the piece and grasp them accordingly. It doesn't need to be in particular order or orientation. The robot could identify them and act them accordingly. And one application for identifying PCB defects using computer vision. This has been used to using all the printed circuit board manufacturing. And in the work area, it could identify the persons are doing different activities and make sure that compliance, safety compliance is happening within the workflow. And in the conveyor belts, it could inspect different products for final inspection. And in the supply chain, it could be used to identify serial numbers or some product information. So you could see the numbers being displayed here, serial number. And into the mining now. In the mining, it could help in resource exploration, surveying, and volumetric estimation, automated mining, which is quite happening now, and sorting, grading different minerals and ensuring the safety and compliance within the mines. So big mines we call these are diggers, which digs the different minerals, and could help identifying crushed jammed crushers, and it could identify different types of minerals in sorting them out. Also, it could help in identifying different volumes in the work site area. Now we see a demo. We see a demo of how a volumetric calculations are done using computer vision. So this needed a lot of surveying. Now this can be done with some camera imaging. that helps for the volume calculations. And next thing is the automated mining, where the mining vehicles are moved by itself and do the exploration. You could see it's mapping the environment, mining environment. Yeah, that's quite interesting. And into the application of medical field. So computer vision could be applied to automated infection and cancer detection, visual guided surgery, surgical helping us semi-automated surgical procedures, and identifying anomalies in bone and structures, monitoring patients, and AR-based medical imaging, helping in biomechanical analysis. So in computer, in the medical field, there's a lot of imaging technologies being used, like X-ray, ultrasound, PET, CT scanners, MRI. So whether it doesn't matter whether this camera, but what it produces in image would be used for computers to see it as an image and recognize something inside. In this case, computer vision is applied to automatically identify cancer cells. So previously, this needs quite a few experts to diagnose. And for identifying different tumors. So it's quite a useful tool for different anomaly detection in medical field. And another example for how it is helping for guided medical surgery, where in this particular scenario, where the tool in relative to the body and the bones and spine are being registered using augmented reality, using computer vision. And then it helps the surgeon to direct and guide it guides the different tools in the surgical area. So it's taking some snapshot, and now it is registered, and you'll see the tools are being now registered into the actual spinal bone image. Now, when the surgeon moves the tools around the area, you could see this cyan color, blue color thing. It moves as well. So it helps the surgeon to exactly identify where the different anatomical things within the body. And it helps in these two images, you would see other different cross section of the same thing. Okay, now we move into the retail application of computer vision, where it could be used for cashierless counters, stock monitoring, customer behavior and pattern recognition, automated store monitoring, and virtual fit-on. In this case, there's a robot which moves around the floor area and identify which stocks are low and let the staff know so that staff can refill them. And in this scenario, cameras do analyze which areas are more hot among customers, which are shown in a heat map, like here, so that this area is more reddish, so that means it's a common area used by people. And blue areas are not so often used. Now we see an application of cashierless store using computer vision and automatically add it to virtual card. So it identified the car. Objects could be detected likewise, but there could be a difficult scenario, like for example, if things are overloaded and there's one on top of another, so someone has to make sure that doesn't happen. Those are the realities in the computer vision. Okay, it's a good example of virtual fit-on. So the camera recognized person's posture, the pose, and then it rendered different clothing. Exciting. Okay, now we come to the computer vision into the self-driving cars. This helps the computer. The typical self-driving car has many sensors. It has a LiDAR sensor, the cameras, radar sensors, and several other sensors around. And this helps to for the car to identify things around that. So in order for the car to drive by itself, it needs to identify the roads it's moving in and the people around, other vehicles around, and identify different signs, traffic signals, sort of thing. And obviously, a demo how a Tesla being driven with computer vision. One misconception some people have is just with GPS, you could drive a vehicle from one to another, but it is not really, because GPS could help in identifying the rough location, but it is not good enough to do this precise thing. It needs to identify things around that, the vehicles, people, signals, there's a lot more. So in this right side images, if you see what the car actually sees, it interprets the world around that. It includes the roads and the infrastructure around, other vehicles, passengers. And another video. different shape. So it has found out the lanes in the road. Yeah, so without the computer vision, I think self-driving car is just a dream. And computer vision is also applied to intelligent transport system, where it tries to understand different traffic conditions, analyzing intersections for traffic capacity management, automated ticketing, law enforcement, that sort of thing. In this case, we would see how a camera interprets the what's happening in the intersection exactly. So it could detect different persons, different vehicles, and it could categorize them accordingly. And it could tell there were this many people, this many cars went through this intersection, so that it needs more capacity improvement, or there was some violation of traffic laws. And this creates a heat map so that it indicates where are the most active areas in the intersection. Exciting. So another quick demo. So in this case, these cameras were able to track all the way throughout the vehicle where it is going. This helps to analyze this complex intersection. Okay, now we into the space. The application of computer vision in space technology, it helps for space exploration, finding new objects, and automating the space observation. And it's helps for analyzing the satellite images for remote sensing. Could from the satellite or disaster or defense or anything like that. These are some satellite images that's being analyzed by computer vision for different geographies and identifying of different minerals as well. In the social aspects, the computer vision is also used for ensuring the security of people, enforcing the law, and identify people emotions, education, training, child safety, that sort of things. This is a video from China monitoring its people around in the city area. So each person is tracked where they're going and what they're doing. It's a bit intrusive, but that is possible with computer. It could track each specific persons. So it's used for automated ticketing. It could create a heat map where the people are mostly moving around. And it can track a particular person. Okay, so it's application of CV for babies, tracking babies, what they're doing while sleeping. This particular camera tracks, it gives alert when the face is covered. It's a quite useful tool for the parents. It could track their sleep patterns. Yeah. And in sports science, it could be used to analyze the sports to improve a sport person's performance. The accurate handling of different objects in the sports field, different techniques could be retrained. A favorite game, cricket. Okay, so we covered almost the internet applications I was going to talk about. We are moving to see trends, computer vision trends. I think with the since it's heavily used in machine learning techniques, so whatever the improvement that machine learning gains would be readily be applied into computer vision as well. And things like generative models, if you know about different kinds of machine learning, generative models, transfer learning, transformers are kind of new techniques to be used in computer vision. And in this concept part, I explained you that this computer vision needs to have a data set for training. It is a very time-consuming, tedious operation. It's out of a computer vision project. It could be the most time-consuming thing unless you have a pre-trained model for that. So that's why the interest for the unsupervised learning, so that we don't need to provide labels for the object. It just see what it is, and it learns like a child. It doesn't need to be told what is this is and other. It will recognize there's a difference, so it could learn from there. And currently, all the computer vision techniques needs a lot of samples, which could work in some scenario, but for certain cases, it's quite impossible. So there's been some research trying to do the computer vision tasks with the low number of samples for training phase. Another trend is the explainable CV model, where currently, whenever computer vision provides some classification, it cannot tell why it does that classification. But with the explainable CV, it could tell what are the reasons why I choose this as a dog. It could say, okay, in this image, I see a tail, I see head, I see certain parts belong to dog. That's why I mark it as dog. But currently, it cannot explain why it detects. And deformable objects like clothes and liquids are candidates for applications of computer vision. Like always, it tries to recognize the different objects under adverse condition with the multi-model fusion, not just using the camera image. It could use different sensors for that too. And computer vision is resource constrained environment like power and memory processing reduced environment is a challenge, I would say. Still, most computer vision tasks need considerable power and power budget. So this demonstration of the explainable CV, where when today we make this decision, but tomorrow's technologies, computer vision itself could explain why I made this decision. And one trend is the pose transfer, where there's a source image and there's a target pose, and it could be transformed into a different posture, which is quite exciting. Like you could be in a different photo and could be turned around into a completely different final outcome. In this case, this lady is wearing a black and white dress, and this dress, blue color dress, is transferred to this body. And another application is another trend is a deep fake, where person's posture and facial expressions are transferred to a different body. That means, and it could look like it is being said or done by the same a different person, which is quite exciting. And plus, like, okay, this person said something like this, but it is not. It may not be real.
Mouth movements are looking great, and eye movements are also
translating. Yeah, so it's exciting and dangerous. And one other trend is the use of event cameras. The traditional cameras use, when it takes the image, it is scanned through all the pixels in the image sensor. So all the pixels are scanned together. But in the event camera, it triggers only the pixel which detects a change in the light intensity. So what it means for the computer vision means it is faster. Like it could go up to like 1 microsecond level temporal interval between one frame to another. And also it could work with the low bandwidth, because it doesn't scan the whole image. It's just if it's a kind of a scenario, the scene is kind of silent, it could be indicating more low bandwidth requirement for the data. And also it could work for high dynamic range, which means it could work for low lighting conditions as well, where traditional cameras are quite facing quite an issue. Let's see some demonstration of that. In tradition, for all the frames and all the pixels are taken, but event-based camera, only the particular pixel is scanned. So this is a technology for the future, and which is available right now, but it needs to be mass produced so that more enhanced, so it is widely available. Okay, now we come to the kind of the final part of the webinar, which is the computer vision opportunities. When we look at the, for some, this curve could be familiar. This is a curve kind of curve provided by Gartner, which is a business analysis company. And they predict what's going to be happening in the different areas of technologies and businesses. And in the innovation trigger, people get a lot of expectation for particular technologies. Then they realize, oh, cannot be done with that. So they lose a bit of trust on that. And eventually they identify, oh, this is not good for everything, but we can do something better in some scenarios. So computer vision, it's there, which is now reaching the plateau. When it reaches this area, which is for mass scale business monetizing. I agree with this diagram for some extent, but I totally do not agree, because computer vision is not a fixed subject. It's growing every day very fast. So certain things that were done. Certain things that were done like 10 years ago now in this area, but there could be the research that is happening right now could be in this area, which could be coming into this area at some point. So as with so if you are a technological innovator, I think the best part for any idea is to see the potential for that to make it a product or solution. So you could ideate a concept and make sure it is researched well. Whether first thing you need to research in computer vision is whether this product or solution can be achieved with current technology. If it is, okay, that's good that you can do it with the current available technology and move to prototyping and product phases. But if it is not, quite could happen, because computer vision is not kind of done subject, not finished subject. So there could be cases you need to go into with hardcore research. And for entrepreneurs, I think there's a lot of business opportunities with what is possible with computer vision. And I think best thing is to glue it with some other holistic solution, not just by itself. And with the right business pitch, I think you can reach to global investors and markets. And also you could leverage the collaboration with universities worldwide and tap into open source and global communities. For individuals, what it means is there are a lot of opportunities for people with computer vision skills. And there's really good salaries, and plus quite likely you could end up with share options if you could join a kind of startups or early stage businesses too. And as for the resources, I think there's a lot available for people, individuals and enterprises, like open source libraries and SDKs. And also there are conferences which you can gain you can see what's the most trending trending things within the computer vision subject. Most common premier conferences are CVPR, ICCV, and WSAV, I would say. And there's a lot of free and some low-cost learning resources nowadays. And also there are a lot of hardware and cloud-based GPs for the computer vision training and testing. So I think we are living in a very interesting time of the time. So you can learn a lot about computer vision and artificial intelligence in general, and you can learn about trends. You can use a lot of open source solutions for making your products, and there's quite a bit of hardware too. So I think it's an exciting time. It's time for us to get the best out of these opportunities available. And I would like to see any questions now.
Hello.
Hello.
I want to
No, I can't really.
Hello.
Hello.
Wait.
Hello. I can't really hear you. Or you can type into the chat so that I can see what your message is.
Hello. Can you hear me now?
Yeah, I can hear you.
Okay. So my question is, when dealing with computation-related research papers and like trying to replicate them, they require large number of resources. Like some research papers are done on multiple GPUs, and it's very hard to replicate them. So do we have like do you know any like online resources that are cheaper, that is accessible for people like Sri Lanka to actually try out them?
I think it's a good question. In my part of the research, I was lucky to have some university resources and some AWS resources as well, but it could be expensive. So understand. I think a best thing, I don't know, it's a low cost thing, but this is an opportunity for collaboration. For example, some foreign universities do have resources to share with. If you could tap into particular university, then there's a possibility you could utilize their computers for your particular purpose. If you come through proper university channels, I think that is possible. If you want to something on that, I can send you some private information. If you send me some email or something.
Thank you. I'll contact you. Thank you.
Okay, I'll try to take a few questions. I think for this question, hello, yeah, go ahead.
Yeah, I have one question. Kalana, thank you very much for this Sri Lanka. There are many entrepreneurs in this computer area. What do you think? What kind of applications would be immediately or in coming next few years would be better to develop in Sri Lanka to get some applications, as you saw many applications, industrial applications and also consumer applications. What do you think would be feasible in Sri Lanka coming years to be developed? That will be very important point for entrepreneurs to start even be develop themselves or be collaborate with other countries to start those kind of applications. So that's the question.
I understand. I think the key thing is as an entrepreneur, there are things that I wish to do as a service, but as an entrepreneur, you need to make sure that it is financially possible and it's generating income after all as well. Otherwise, the business is not going to sustain. So one thing you need to look at is like what things people willing to. That is an area that I would say to spend on. One possibility is like for luxury items or retail, because people are spending anyway some money on that. So there's a possibility to get a part of that. So I think areas like retail or travel area, the tourism. I think tourism is a really great example because it could, if you do something, if you come up with some product for tourism, it not just help you, it helps the whole tourism industry as well. And also the retail, there could be some retail setup could be quite beneficial.
Yeah, great. Thank you.
Actually, it's for the community, it's actually up to the individuals, but it is just my opinion. I think yeah, it's asked question whether if we carefully select the data set, whether it would improve. It would improve, but as you said, it is going to be biased towards that particular data set, and which could be fine if it is only the particular data set we actually see in the testing environment. I mean, when it is being really used as well. But if you are going to expect something other than that, it's going to be an issue. What are the effects of speed of detection in camera? Not quite clear. Neil, if you could explain what your question is, if you're around. Some ask if I want to shift my career to AI side, what would be the first step to follow? I think first thing is you need to get some inspiration. What are the possibilities? Motivation would drive you, and you need to learn to few fundamental things like some mathematics and a bit of machine learning, because machine learning is one of the key foundation of AI, modern day AI. Okay, so I think that's all question. Anybody has any other question? Looks like not. So is there any? Okay, what are the job opportunities in Sri Lanka in AI and industrial robotics field? Actually, that's a good question. First thing, I haven't searched by myself in Sri Lanka because I currently live in Australia. So, but if I were to do the same, what I would do is I would get a list of companies who are involved in AI, artificial intelligence, and see what they're doing and whether I would have any skills skills required for them. If not, I could upskill my knowledge to that, so that I would be a preferable option when they're considering. Yeah, sure, I can share my email address.
Yes, thank you very much, Dr. Kalana, for your very informative and interesting talk. So I have a small question that is regarding that the thing that however in this deep learning we find that this overreacting or that overfitting is also a problem, because that when we consider this that autonomous vehicles and like that, however this overreacting is also, it is very harmful meters that we can identify to minimize this, like selecting input is one solution maybe. So other than having a
I think yeah, I understand. Yeah, I think one solution mainly comes from the input itself. One major technique is like you could introduce some noises into the actual input. So and also when you are splitting the test and training sets, it's very critical. You have some unexpected things in the test set as well.
Yes. Yeah, and this size of that architecture, and like that we can consider something like that. No? That
Yeah, I think into the architecture, probably if we could integrate some noise component, which could be really handy, so that not just within the input image itself, input things itself, but as a part of the architecture, it could create noises so that
yes.
yeah, it's invariant to them, which is quite a similar technique used in computer vision for different or viewpoints, because in the training data set, we may not have all the viewpoints, but internally, what some similar operation it does is to slightly move it before it's being feed in, so that we could create more variations within the inputs.
Yes. Okay.
Okay, so if
Yes. Once again, I would like to thank you, Dr. Kalana, for your participation and having this very interesting talk. And we hope that you will join with us in our future events.
yes, yeah, I think it's a great activity, and I'm pleased to engage with this webinar. Thank you for the opportunity. Have a good day, everyone.
Yeah. Yeah, so I will finish this and hope that we don't have any other questions. Yeah. Okay, thank you. Good night and stay safe.
Thank you, everyone.